study on microcalorimetric study of oxygen absorption on graphite supported iron rhodium particles, and its contribution from Penn State University, work by Jonathan Phillips and Bob Gatte, and Bob Gatte will present the paper.
I'd like to talk about some of the work that I've done as part of my doctoral thesis at Penn State University under Dr. Jonathan Phillips. What we were interested in is studying the structure of, in this case, a graphite-supported iron rhodium catalyst system. And the reason we're interested in this particular type of a system is, as was mentioned yesterday, as one of the talks yesterday, these types of noble base metal alloy systems exhibit very interesting chemical and catalytic properties, and they're also somewhat difficult to characterize since they're typically produced as microcrystals on hydroxylated supports. So what we attempted to do was to somewhat simplify the system, take one step back, and to look at what we consider to be a model system, and that was a non-interactive graphite supported system, and to study the morphological changes that took place in the system as a function of oxidation and reduction treatments, and then try to back out what this meant and how this could be related to more realistic oxide-supported catalytic systems. The approach, as I said, was to use an inert graphite substrate, and we used a stoichiometric organic precursor compound as our starting material. In this way, we started with the stoichiometric ratio of metals in all of our metal clusters from the outset of the experiment. It was a 1-to-1 ratio of iron and rhodium. And we loaded the graphite to about 5 weight percent, which gave us large particles, and this limited some of the small particle complications in interpreting the data. We used Mossbauer spectroscopy X-ray diffraction to look at the bulk characteristics of the metal phases, and transmission electron microscopy to try and get an idea of the microstructure. And then the work that I'm going to talk about today, the use of differential adsorption microcalorimetry to study the surface of the supported metal particles. Now, on the basis of the X-ray and the Mossbauer work, what we concluded, without getting into the details of the data, we concluded that when we oxidize these supported metal particles in any state, once we oxidize them at high temperature, about 200 degrees C, what we ended up with was a localized decomposition of the iron and the rhodium into separate zones of iron oxide and rhodium oxide. They existed essentially as microcrystals inside larger, what I'll call bimetallic oxide agglomerates. They were particles, larger particles consisting of microcrystals of separate iron oxide and rhodium oxide. If you then take these segregated oxide catalysts and reduce them at low temperature in hydrogen, typically around 100 degrees, what you end up forming is a catalyst that was basically 100% reduced. All the metal was in a zero valence state, but the segregated zones retained their integrity. And so we ended up with segregated gamma rhodium and alpha iron particles inside larger agglomerates. And it was apparent that we had distinct but very adjacent metal, different types of metal particles. And after the high temperature reduction step, which is typically a 400 degree hydrogen treatment, we ended up with a BCC uniform alloy, stoichiometric alloy particle after the high temperature treatment. So on the basis of this, what we tried to do was to look at the chemical behavior of this material. We thought we had a clear picture of what the bulk phase changes that took place as a function of oxidation and reduction were. Now we wanted to see what's the surface of this particle look like, and how is this related to the chemistry that it might exhibit. We wanted to look at the phase segregation and possibly relate the phase segregation that we were witnessing to some type of support effect that might be exhibited in an oxidic supported material. In addition, we wanted to examine the possibility of a surface enrichment as a result of this oxidation treatment. And a technique that we decided to try and use to establish the nature of the surface was differential adsorption microcalorimetry. The calorimeter that we developed was able to measure real differential heats of adsorption as a function of coverage. And in addition, we were able to get adsorption kinetic information for each dose and changes in the kinetics as a function of coverage, and also some heat evolution dynamics. And I'll just briefly describe the system. The calorimeter cell, what the calorimeter actually does is we run a typical chemisorption experiment and simultaneously measure the heat that's evolved as the gas is absorbed on the catalyst sample. The cell is a flat, pancake-shaped glass system that's connected to the other volumetric pieces. The sample typically lies in a bed on one end of the calorimeter disc, and this disc is then surrounded on either side with thermopile sheets and then large aluminum blocks that act as our heat sink. Gas is admitted through one end, is absorbed in the bed, the heat is evolved and then is transferred through these thermopile sheets, and what we measure then is a heat flux as a voltage difference between what we see with this sample and a reference sample that's essentially a blank, an empty cell. And we can measure the actual amount of heat that's evolved and that passes through these thermopiles as the adsorption process and heat flow takes place. Overhead view of the calorimeter, it's just a simple adsorption system. Our dosing volume is this piece in the center, and the reason that we can get these kinetic measurements is that we have incorporated barytron capacitance manometers as part of the dosing volume, and therefore we can actually measure the change in pressure dynamically during a dose, and then look at the shape of the pressure trace curve and get an idea of the kinetics, qualitatively look at the changes in kinetics of absorption as a function of coverage. Now what we wanted to do was to look at the surface chemistry, and what we chose as our adsorbate, in this case was oxygen. We measured the differential heat of absorption of oxygen on each of the structures that I described previously, and also looked at the kinetics of the oxygen absorption as a function of coverage. I'm going to dwell on the heat data today for the sake of time. What we found was that when we adsorbed oxygen on what I'm going to call the low temperature reduced phase, the segregated reduced metal phases, what we ended up seeing was that the absorption, the heat trace or the heat profile was essentially the same as what you would see on monometallic iron. Whereas if we adsorbed oxygen on the previously high temperature reduced and alloy particles, we ended up the system exhibited behavior that was not like either of the monometallic extremes, and it was very characteristic of what we believe is a bimetallic, uniform bimetallic alloy phase. Now this is a plot of differential heat of adsorption versus coverage for the two monometallic catalysts. Now I didn't mention at this point. The catalysts were typically loaded at about 5 weight percent. We're looking at a 5 weight percent rhodium on graph foil and 5 weight percent iron on graph foil. The iron data, you can see that they're very different heat signatures, is what I'll call it. Iron is fairly steady for a long period of time, up to about 3/4 total coverage. It then drops off rather dramatically until you reach the physical adsorption region, and then we're measuring physical adsorption heats down here. The integral heat of this, if you integrate the area under here, you can get an idea of the integral heat, and it's about 130 kcal per gram, which is what you would expect for oxidation by forming iron oxide essentially on the surface of these large iron particles. In contrast to the oxygen adsorption on a supported rhodium particle, the heat basically drops off from the start and tends to stabilize to some extent for a short period of time and then continues to drop until you completely saturate the surface. In this case, the integrated heat of adsorption by the area under the curve is about 67 kcals per gram, which is substantially higher than the heats of formation of any oxide phase of rhodium. And so we believe that in this case we're actually forming a surface, an adsorbed layer, a true chemisorb layer on the surface of rhodium, supported rhodium particles. The important point here is that the heats over the entire range are substantially different between the two metals, and the shape of the curves are substantially different between the two metals. Now if we compare these data with the data from oxygen adsorption on the bimetallic sample after the high temperature reduction alloying step, what I've done here is I've normalized everything to correspond with a total oxygen coverage of 1. What you see is, here's that iron data and the rhodium data again. The bimetallic data falls between the two extremes throughout the coverage range. It starts a little higher working towards the iron extreme at low coverage and tends to fall towards the rhodium and at high coverage. But throughout the coverage range, we're looking at adsorption that appears on the basis of this to be oxygen adsorption on a bimetallic surface, a surface that consists of both types of atoms. These are some TEM pictures of the particles after this high temperature alloying step. They appear to be very uniform, nice, almost single crystal particles that are sitting on this graphite substrate. In contrast now, if we take these particles and oxidize them to 200 degrees, the morphology of the particles changes completely. And you see what I believe are these segregated zones of these different oxide phases inside these large bulk particles. There also appears to be somewhat of a shell around the outside that may or may not be an artifact of the technique. But the morphology is very different. You can clearly see these separate zones of the different oxide phases. Now, if you then take this sample and reduce it, subject it to the low temperature 100 degree hydrogen reduction, morphology changes again. Particles tend to change their shape to some degree, but they still exhibit this zoned behavior, which tends to indicate that we still have these segregated metallic zones, and still inside the same larger particles there are some structural, some morphological changes that it's not clear exactly what this means. But in essence, we've still retained this segregated nature of these metals. Now, what I've done here is I've looked at, I've compared, this is that same bimetallic data that we saw a few slides previously. If we've then oxidized and re-reduced at low temperature and then absorb oxygen on the surface and measure the heat. This is the heat profile that you see on the sample after this oxidation and low temperature reduction. The uptake is increased by about a factor of almost 4, and the heat is substantially higher than that exhibited by the bimetallic surface. And if you compare this profile with that of pure monometallic iron, they're almost overlays of one another. There tends to be a little bit of scatter, and the points tend to fall slightly below that of the monometallic extreme. But it appears as though we're absorbing oxygen on a surface that's primarily iron. And so we think this is one model that we can use to explain the dynamics of this behavior that we're looking at. After the high temperature reduction step, we've got these nice uniform crystallites of BCC bimetallic iron rhodium alloy. After the high temperature 200 degree or above oxidation, these nice particles tend to segregate into smaller zones of iron oxide and rhodium oxide, which still exist inside the same larger particle, but the surface tends to be enriched in iron. And I think I'm basing that on the heat data that we got on adsorption of oxygen onto this structure, which tended to show that we had a surface that consisted primarily of iron. And on the basis of all the work that goes into this model, the whole cycle can be repeated as many times as you want, and you can always return to the various phases by proper temperature and gas phase treatment. And as a conclusion, future focus of the work would then lead us to try and actually, now that we've got an idea of what the structure of the surface is, we want to possibly look at the surface chemistry, various reactions over the surface of these particles in their various states. In addition, you can extend this to the morphological behavior of other bimetallic systems, and also eventually examine the effect of support interactions in how an oxidic support, an oxidic substrate would affect the morphology of these supported bimetallic particles. And at the end, I'd like to just acknowledge the support of the National Science Foundation, the Pennsylvania State University, and acknowledge the advice and guidance of my advisor, Jonathan Phillips, and thank you for your attention.
A couple of quick questions, please.
Have you run a physical mixture of the pure monometallics on carbon and gotten its heat trace?
No, we haven't, and that's a very good question. That's something that we've considered. And it's hard for me to say what I would expect to see. It depends. The absorption in a case like that is going to, it's possible that you may see a trace similar to what we saw on the bimetallic alloy particles, but that would only occur if the kinetics of the absorption process on the two metal phases were the same, and you had exactly the same amount of exposed metal surface area, I would think. But no, we didn't run that.
What is the stoichiometry of oxygen absorption on rhodium at room temperature?
Okay, in the case that we ran, the absorption of the stoichiometry of oxygen on the rhodium particles was low, below 1. It was about, I think, just slightly below 0.7 oxygen atoms per surface rhodium. In the case of the iron, it was up around 3.5 oxygen per surface iron atom. And that would account for the increased, fourfold increase in the adsorption uptake on the what we believe to be a preferentially higher surface.
And the heat of adsorption you said did not agree with any known phase of rhodium?
As far as I know,
Was it much greater? Or?
it was significantly greater, almost double. And this also corresponds to thin film studies that people have done in the past. I think Brennan Hayward and Shrapnel and some of the early work studied oxygen, found similar results.
Okay. In the interest of time, thank you for your presentation. The next contribution is on exhaust catalysis development for methanol fuel vehicles, formaldehyde oxidation. It's a contribution by Bob McCabe and P.J. Mitchell from the GM Research Laboratories.
This is part 3 in a study of exhaust catalyst development for methanol-fueled vehicles. It deals with formaldehyde oxidation. The previous 2 parts dealt with various aspects of methanol oxidation. And again, I want to acknowledge my co-worker, Patricia Mitchell, and this work was done in the physical chemistry department at General Motors. There's a lot of environmentalists that see methanol-fueled vehicles as an alternative to gasoline, as a clean-burning alternative to gasoline. This fact notwithstanding, there are emissions concerns with methanol-fueled vehicles, chief among which is formaldehyde. It's a major concern both because of its potential health effects and also because of photochemistry. It's photochemically quite reactive. So we felt that this would be something that would be of interest to look at. And before I get into the study, I'd like to point out that there are 2 sources of formaldehyde that can come out the tailpipe of your car if you have a methanol car. One of these is what I call direct, and that's formaldehyde that's produced in the engine by the partial oxidation of unburned fuel. Carries through an exhaust, passes over catalyst unconverted and out into the atmosphere. The other is indirect formaldehyde. And this is produced by partial oxidation of unburned fuel, methanol, over the exhaust catalyst. And in our previous laboratory studies, I focused primarily on this indirect formaldehyde production. And in fact, in this next slide here, I can give you an example of what we see for various catalysts. Here we show results of formaldehyde production over 5 different catalysts. These are all supported on gamma alumina, as are all the catalysts that I will speak about today. A couple things to note. What we're doing here is in the laboratory, we're reacting methanol, CO, and oxygen over these various catalysts and looking at the formaldehyde yield as a function of temperature. What you see here is that the yields of formaldehyde are quite different for these different catalysts. And in fact, this indirect production of formaldehyde can be quite extensive given the large emissions of unburned fuel that are characteristic of these cars. Secondly, you notice that all the curves have a maximum in the formaldehyde production. I think this is indicative of a series-type reaction mechanism where your methanol is first partially oxidized to unburned fuel, to formaldehyde, and then the formaldehyde can further react to form CO2 and water. One of the things we found that 2 of the more attractive catalysts for methanol oxidation were platinum and silver-based catalysts, which, as you can see here, give very low yields of formaldehyde. But this data tells us nothing about the activity of these catalysts for the direct conversion of formaldehyde. And so that was the basis of this additional work that we've done. Experimentally, the direct formaldehyde oxidation is difficult to study because it involves having to make gaseous formaldehyde, and your options are either starting from paraformaldehyde or starting from a formalin solution. Neither one was very attractive to us because of the difficulties of maintaining formaldehyde in vapor state. So as an alternative, we utilized a pre-reactor to generate formaldehyde by the partial oxidation of methanol. And then we fed that formaldehyde from the pre-reactor into a test reactor where the catalysts were evaluated. And the scheme is shown here. Helium is fed through a methanol saturator, then we add oxygen. It goes up in upflow fashion through a pre-reactor, and then the product stream from that reactor is fed directly into our test reactor. Products from that are analyzed in normal analysis training. This table shows the composition of the pre-reactor product stream. And at various times in the study, we used two different catalysts, one being of palladium, the other vanadium, again, both supported on gamma alumina. In the case of the palladium catalyst, we used that where we wanted to...
We're getting behind now. Thank you very much. So please. And
we could generate, starting from about 2.2% methanol, we could generate about 0.02 to 0.025% formaldehyde, 200 to 250 parts per million. On the other hand, by using a vanadium catalyst at somewhat higher temperatures, we could get higher concentrations of formaldehyde, 600 to 750 parts per million. But we also inevitably had CO formed as a product. But this is actually not bad, because in a real exhaust stream, you'll always have CO there along with the formaldehyde or whatever organic species you have. Now, what I will show next is I'll gradually put this figure together. I'm going to show results of 5 catalysts, same 5 that we looked at previously for methanol oxidation. And we'll show results of formaldehyde oxidation. But in each frame here, for each catalyst, what I will show will be results of 3 separate experiments. The first involves just the oxidation of formaldehyde, given by the solid curve. The second is the conversion of formaldehyde in a stream that contains both formaldehyde and CO. And thirdly, just for comparison purposes, we show just the conversion of carbon monoxide in a feed that contains only CO and oxygen. Now, for the case of the platinum catalyst, what you can see here is that for formaldehyde oxidation by itself, platinum is extraordinarily active. Even at room temperature, we got significant conversion, and by 400 Kelvin, we were essentially completely converting the formaldehyde. However, when we looked at formaldehyde oxidation in the presence of carbon monoxide, we found that the results were quite a bit different. In fact, we got complete inhibition, suppression of the formaldehyde oxidation until we reached temperature